There we go. That's sort of what we're trying to fix thing. All right. Good morning, everybody. My name is Henry Price. I'm an undergraduate student from Lehigh University. I work under Professor Himanshu Jain at Lehigh University. And I spent my summer at the University of Montpellier in France working on 3D printing of silicon oxide carbide-based polymer derived ceramics. So before I get into the specifics of what I did, I think it's important to establish a baseline of the technologies that I use. So firstly, I was using LCD 3D resin printing. So as opposed to an extrusion-based 3D printing method, this uses a vat of a liquid resin, and which is selectively cured in a certain shape to form a layered final part, as you can see in this animation here. The second main technology, which you're probably all familiar with, is pyrolysis, which is the heat treatment of this pre-ceramic polymer, which I printed to convert it to a ceramic at elevated temperatures. So now an overview of what I worked on. So the goal was to induce and control porosity in a proof of concept 3D printed polymer derived ceramic. And what I was specifically working on was a contribution to the France ANR funded project 3D printing of ceramic membranes for wastewater treatment. So while I was not creating the end membrane, I was creating a proof of concept 3D printed part that would contribute to that project. And so what the testing I conducted was seeing how changes to the resin system, as well as additives, which are other materials added to that liquid resin, impacted the macro and the microstructure of these samples. So resin chemistry plus additives, and then the evaluation that I conducted was after printing and after pyrolysis. So just to give you a quick overview of some of the issues of things that could cause a failed test would be, so after printing, sometimes the print would not fully complete, and sometimes if the resin was too viscous, it could not print at all. And this is, I'll get into it more specifically later, but this is affected by the chemistry of resin as well as the additives. And now after pyrolysis, one of the main issues I was working on is cracking of the part, because as you know, during pyrolysis, there's gas release from the sample, and that it needs a place to go. So oftentimes the samples will crack. And the two main types of mechanical failure after pyrolysis were what I call delamination, which is it's layered cracking, which was between print layers, and more randomized cracking, which is along that kind of vertical axis. So in manipulating the resin chemistry, I don't want to get too into the weeds here with the molecular chemistry, but I had two main variables. So I was changing the cross-linking agents, the things that made it photoactive, and keeping constant the pre-ceramic polymer precursor, which was siloxane, as well as a solvent. And so these affected the end part slightly differently. So the main difference is that this, what I refer to as VTMS, which is an initialism for one of the molecules there, has a greater degree of cross-linking as compared to what I will refer to as HDDA. And so that's the main difference for all intents and purposes in this project, is the degree of cross-linking between these molecules. So now on the additives I used. So one of them was PMMA, and the purpose of adding PMMA is as a sacrificial filler during pyrolysis. So PMMA is an organic polymer, and so therefore at the heightened temperatures of the pyrolysis process, it will be removed. And so this diagram kind of shows the general theory and goal of this project, which was to suspend these PMMA beads in a printed part. I'd add them to the resin. It would be printed, a 3D printed part, and have these beads suspended in the actual sample printed part. Now, during pyrolysis, these beads would be removed, leaving behind cavities, which in theory, could be manipulated to create some kind of interconnected porosity with end goals and membrane applications. So the other additive is I used was alumina nano powder, and this was used to improve the mechanical properties. So this provides structural support to the actual silicon oxide carbide matrix. So a bit on the pyrolysis. So the first thing we did was conduct TGA on the PMMA itself to verify at what temperature it would be completely removed. And this was found, as you can see, to be by 400 degrees Celsius. And so this value informed the pyrolysis treatment schedule that we used. So you can see initially there's a plateau at 200 for just to make sure the sample is completely cross-linked. There's another plateau at 400, and this is to ensure that all of this PMMA is removed. And then obviously, of course, at the top, we conducted pyrolysis at 1,000 degrees. Now, a bit on the PMMA beads I used. So these were micro beads. I did some image analysis of some SEM images to get an idea of the ranges of the diameters of these particles. And you can see it's a pretty wide spread, but it centers around 60 to 70 microns in diameter. And so this would affect the pore size after pyrolysis. So we're working on a scale of micro pores. And just a brief background check, we conducted FTIR to make sure we did have PMMA, and we did. So now a bit on some of the initial results. So just to be clear, the title refers to the two different things I manipulated about the printing process. So if you'll recall, the HDDA, that was one of my cross-linking agents. So that's part of the resin chemistry. And the PMMA, this is the additive that I was using in this test. So obviously I printed first without any PMMA, and then I added increasing amounts of PMMA weight percent. Initially, one of the most striking results, most important results, is that over 20% PMMA, the prints consistently were unsuccessful. And so why this was because of the increased viscosity of the resin itself, that the increased amount of beads made possible. So as you can see, at 30% PMMA, these prints are not a full height. There's large cavities compared to a successful print, which would be a full height cylinder. As you can see, I was printing cylinders with a 15 millimeter diameter and a 5 millimeter height. And so you can see on this image on the bottom right, this is the resin vat after the print. As you can see, all the resin is separated around the outside. The printing area is in the center there. And that's because the viscosity was so high, it could not flow completely to cover the surface, and therefore could not provide enough resin to form a new build layer. And also, as you can see, there's some edge definition issues with the PMMA, but those were alleviated by some slight restructuring of the printing parameters in the printer itself. So now moving to post-pyrolysis. Now, apologies if you can't see it so well. It did turn black, so it's kind of hard to see in a darker background. But this is a side view of one of the samples with 10% PMMA. And what I would like to call attention to is these horizontal cracks, what I call delamination. And so this is separation between those actual build layers caused by the gas release during the pyrolysis process. And so this was consistent in all samples using this HDDA resin chemistry. Even with no additional PMMA, there is a crack all the way across the sample. So now a bit on the microstructure. So this is a view of the top of one of the samples with no additives post pyrolysis. And as you can see, it's quite a rough surface with potentially some inherent porosity. So this would be porosity without any additives for induced porosity. So this is an interesting finding, and one of the I believe that this is one of the reasons why it was had such prevalence of that delamination, that mechanical cracking, because there's a large amount of porosity, meaning a large amount of gas needs to go somewhere. So now, in the addition of alumina, just a qualitative review of the samples revealed that they increased the stiffness, increased the strength of the 3D printed samples, but however, now only above 2.5%, we began to get cavities in the prints. And again, I believe this is due to the increased viscosity. And the reason why this is a problem beginning at such lower weight percentages, I believe, is because of the size and morphology of this alumina nanopowder. It's a smaller powder, so more surface area to volume ratio. And also, I believe it was not spherical, so could have had more surfaces to be caught on each other and increase that viscosity. Now, post-pyrolysis, these were generally more successful, but still, as they used this HDA resin, they still had some delamination issues. Now, I'm going to switch to the other resin chemistry system, so this VTMS. Generally, again, this is a qualitative evaluation. I did not conduct any mechanical testing, but they increased the stiffness of these prints. However, the viscosity issues with the printing of higher weight percentages of aluminum persisted. You can see there's a cavity there. But so it revealed that we should stick to these lower weight percentages. So now, post-pyrolysis, so the delamination issues were less prevalent in this VTMS-based resin. And I believe it's because of the what I mentioned previously at the beginning, which was the increased cross-linking caused by the resin chemistry here. However, there were some instances of the more randomized cracking, as you can see in this top right here. However, some of the most successful samples, by successful I mean limited cracking, good cohesion of the sample post-pyrolysis, was with the addition of some 10% PMMA and low percentages of alumina, resulted in generally successful samples. So now a bit on the microstructure. So again, this goes back to this increased amount of cross-linking, which I think may have contributed to this more uniform, more smooth sample surface that you see. So this is an unpyrolyzed sample and a pyrolyzed sample. And just a quick, see if it shows up, a quick comparison to the microstructures of the other resin chemistry based samples, again, unpyrolyzed and pyrolyzed. You can see how much rougher these other samples are. And these are on similar scales of magnification, so they are an accurate comparison. Now some macro scale views. So as you can see, at 10% PMMA, in a side view, we really don't see this delamination. And also there's minimal large scale cracking in the samples. There were some slight cavity issues during printing, but generally a more successful sample overall. Now, it's important to make note of the aspects of one of the goals of the project, which was to use this PMMA to induce some porosity. So this is a really helpful image to show exactly what's happening on this micro scale. As you can see, this is a pyrolyzed sample. As you can see, these are the pores, the vacancies caused by the removal of those PMMA beads. But the important thing to note is on this image here, you can see that the distribution of these pores from the PMMA beads is not uniform throughout the sample. You can see in this area here, it's quite concentrated and they are actually touching, but however here, they're much more widely spread out. And so this kind of leads to the conclusion that there is not interconnected porosity at these lower weight percentages of PMMA addition. And this gets to the heart of one of the issues with this process that I kind of worked with all summer, because you're balancing the amount of the weight percent of additive you can add to the resin, which will increase the viscosity. However, you need a certain amount of this additive to get enough pores to have interconnected porosity. Just to do some quick verification, I did conduct some mercury porosimetry testing. It did reveal no measured porosity. However, I believe more testing in this avenue is needed because there could be some issues with that testing method. So the conclusions from my work, I'll go. So first on the resin chemistry, those with HGDA cross-linking agent have some inherent porosity, as you saw, but generally on a macro scale have much more delamination, mechanical failure. The VTMS samples, they have less inherent porosity. However, on a macro scale, they are more successful after pyrolysis. And with the addition of aluminum, this does improve mechanical macroscope properties. And again, I must add the caveat that this is not a quantitative evaluation. I did not conduct mechanical testing, but from a qualitative analysis, this was consistent. And the optimal percentage was 2.5 weight percent, so quite low. Higher than that results in printing issues from the cavities and the high viscosity. Finally, PMMA, it does create pores, but at the weight percentages that were successful in printing, this is not high enough to create interconnected porosity. Further, and this is in agreement with some literature as well. And in just looking at it, you need higher amounts of additive to get that interconnected porosity. However, from a macro scale, there was success in improving the mechanical properties over the summer, improving the lack of cracking. So more work is needed, particularly on this induced porosity avenue. But a fair amount of progress was made this summer on the printing and the proof of concept. So some acknowledgements. I'd really like to acknowledge Dr. Christelle Salome, and that's me with her research group on the right. I had a wonderful time in Montpellier this summer. They made me feel really welcome, and I was able to get a lot done. I'd like to thank Dr. Himanshu Jain, my supervisor at Lehigh, and of course the European Institute of Membranes, which is where I was working, PIRE, and France, ANR, which provided funding for the research project for the PhD student with which I was working for most of the season. So thank you so much for your time. I'll now take some questions.